Hi, we start to learn differential equations, and in this lesson we will study its basic concepts. A differential equation relative to y from x is an equation that contains at least one derivative of the function y, in which it is required to determine the function y itself. In general, we can write it as follows. There is some expression f, it depends on x, on the function y itself, and on its derivatives. For example, the first derivative, the second derivative, and so on up to the nth derivative. This is equal to 0. Then we can say that we have a differential equation, or the nth order. That is, the highest order of the derivative shows the order of the equation. If our equation depends only on the first derivative, then we would call it a differential equation of the first order. The function y of x is called the solution of a differential equation. If being substituted into this expression, it gives us an identity. For example, let's say we have such a differential equation. Y 2 dashes minus 2y dash plus y equals 0. It is required to prove that the function y equal to xe to the power of x is the solution to this equation. In order to prove, we need to substitute this function into this equation. To do this, we need to calculate the first derivative. The first derivative is defined as derivative of y multiplied by f. That would be e to the power of x plus xe to the power of x, or take out e to the power of x. It will be x plus 1. Now let's define the second derivative. We do it the same way. That would be e to the power of x. X plus 2. Now let's substitute these expressions into these differential equations. Instead of the second derivative, let's substitute this e to the power of x plus 2 minus. Instead of the first derivative, we put this expression 2e to the power of x plus 1, and plus y from x, and we have xe to the power of x. Now let's expand the brackets. Ex multiplied by x, we get xe to the power of x plus 2e to the power of x minus 2xe to the power of x minus 2e to the power of x and plus xe to the power of x. Let's see how these components mutually annihilate. In the same way, these components cancel each other out. Thus we get 0 on the left and on the right. That is, we got an identity, which means that this function is indeed a solution to this equation. But, for example, the same equation has another solution. If you take a look at the function y equals e to the power of x and substitute it in the same way, then you will also get an identity. Thus, a differential equation can have more than one solution. These solutions that we have found are called particular solutions. Thus, we have introduced the concept of a general solution. The function y equal phi of x, which depends on x, also depends on some arbitrary constants c1, c2, and so on, cn. It is called the general solution of a differential equation if any particular solution can be expressed in terms of this function, by variations of the constants c1, c2, and so on, cn. For example, in this case, our general solution will look like this. Y equals c1e to the power of x plus c2x ex. It will be the general solution of this equation. Indeed, we can express both of these particular solutions in terms of this general one. For example, if we assume here that c1 is 0 and c2 is 1, then we get this solution. Or if we put c2 is equal to 0 and c1 is equal to 1, then we get this solution. Let's consider some differential equation. In general, f from x, y dash, and so on, yn is equal to 0. If we can express yn from this equation and represent this equation in some form, ynth derivative, that is, the highest derivative, equals f from x, y dash, and so on, up to yn minus 1 derivative. If we can write this equation in this form, then we can say that the differential equation is given in normal form. We will solve both equations in this form and in this form. By the way, the process of solving differential equation is called integration of equations. And the function y from x is called either a solution or an integral of this equation. It is generally said that when the function y is expressed explicitly, that is, a function in the form of y from x, then it is usually called the solution of a differential equation. If the function y is given in some implicit form, for example, some function g of x, y is equal to 0, that is, the function y is given in an implicit form, then we can say that y is the integral of our differential equation. And finally, let's consider the simplest differential equation. This is a differential equation of the form yn equals f from x. That is, the function on the right depends only on x. To solve such an equation, we need to integrate the function f the nth number of times. For example, let's consider this equation, y dash equals f from x. Then, to find the general solution to this equation, we simply take the integral. We know the integral of the derivative. It will just be a function of y. Integral of the function f of x, fx dx. After calculating the integral, we will have some antiderivative plus some constant c. For example, let's solve such a differential equation. Y dash equals, let's say, cosine x. Then y equals integrate. The integral of y dash is just y, the integral of the cosine. We know that the integral of a cosine is a sine. Get the sine x plus c, and this function is the solution to the original differential equation. It is given a general solution. Now let's take a look at a more complicated example. Let's say we have y two dashes equals x. Let's try to solve it. To solve this equation, we respectively need to integrate the right side, but twice. We do it consistently. Integrating once, the integral of y in the second derivative is y in the first derivative. The integral of x dx will be equal. Integral x dx, as you know, will be x squared divided in half plus some constant c. Now, you have an equation y dash equals this expression. We integrate again in order to find y. We get y equals the integral from this expression. Integral of x squared divided by 2 plus c dx. Let's integrate. The integral of x squared is x cubed divided by 3 and halved. That is, we have x cubed divided by 6. The integral from c is some constant, will be equal to c times x. Plus, we must add one more arbitrary constant, since we have an integral. Let's call it c2. And let's mark this constant as c1 for convenience. Thus, this function will be the general solution of the original second-order differential equation. If we had a fifth-order derivative here, for example, then we would accordingly have to integrate 5 times, and we would get a function that depends on x, and 5 arbitrary constants. This video lesson is over.